Hello everyone. Today I will introduce the exercise about the multi-phase surface tension. Firstly, as I sent the message to you yesterday, I will introduce how to download the latest source code from the GitHub. Now I share screen. Okay. This is the website GitHub about the code source. Here is the website address. I have sent it by the WhatsApp to you. And here, this is the first one, and this is the second one. And about the surface tension case, we just need this one. So here are two source code. You can download this first one. This is source code. You download it, and on your desktop you can see this folder. And then you decompress it. And then you use your CMake. Firstly, you delete this old file. You delete it, and you need to create a new folder to store. But I will name it English building. Sorry, building 2. Build is okay. And this folder is the decompressed one. And here you need to choose the address about this multi-phase source code. I can show you. Choose this one, and then you need to choose this build file to store the building files. This is your desktop. Choose this file, and now you can directly click this configure. Because in my computer, I install the Visual Studio, the version is 2017. And in your computer, I suggest you should better choose this version. And then you choose, click finish. What happened? Okay, close. Oh, okay, mistake. You should open this Sphinx multi-phase and this one. Okay, now it's and then you click the generate. And finally open the project. Okay, now it's okay. Now you can see all the code in your ways. And this case, test 2D weighting effects is the case we need to use about the surface tension. And if you want to write this case, you should right click and choose this, set it to run it, and then you should change here. There are 4 options. debug mini size release and release with debug information. I suggest you choose the last one, release with debug information. And now all things are okay, and you can run this code. This is how to say make the source code file you download from the GitHub. And now we will start to introduce about this case for code. Firstly, I will introduce about the result of the surface tension. This screen you see is the result about the test case weighting effect. This case, and here are three parts. The first one is the solid wall boundary. It's red, you can see it, and because we simulate two phases, one fluid part is the water body, and another one is the air body. Air body is this blue one. Water body is this white particles. And now I run it. You can see the water body, its shape has been changed due to the tension force from the air body. Okay. Then I will introduce the code. Of course, here are two case file. One is the called .cpp file. This is about the algorithm we use in simulation, and another file is called case.h file. In this file, we define the geometry of the bodies. You should right-click and open it. And now I will introduce this code one line by one line. Firstly, here is the parameters about the geometry. The first one is the tank length. And of course, there are many defined green lines. I have write on it to explain what this code means. The third one is the particle spacing. It is calculated from the tank length divided 40. Of course, if you want to smaller particle spacing, you can change it to 18 or 16. They are okay. If you change it in reality, you just change the particle diameter. Here is the BW. BW means the width of the boundary. In pair view, you can see here, the red one is the wall boundary. Here conclude 1, 2, 3, 4, about 8 layers of surface particles. If in SPH simulation, the wall boundary should contain at least 4 layers of particles. So here, BW should be equal to particle spacing multiply at least 4. Okay, and this domain bounds of the system. This is the computational domain size. This domain size should contains all these 3 bodies, because all these 3 bodies are computed in the system domain. So When you define this computational system domain, its size should be larger than the total of these three bodies. And here, this is the material properties of the fluid. Because there are two fluid bodies, air and water. The first one is the density of the water. This value is equal to the real density of water, because in our simulation we use dimensionless values, so you can not say its unit, you just say its value. This one is the reference density of the air. This one is the gravity. Here you can see the gravity is 0 because we ignore the gravity on water and air, and you can change this value to 1. So the water and the air will be forced by the gravity. Here is the characteristic velocity, and this is the sound of speed. Sound of speed is 10 times this characteristic velocity. And then this is water viscosity and air viscosity. Of course, you can change both of them. And here is the contact angle. This one, you can see it's 100 divided 118 and multiply the pi. What's this parameter means? You can see here. Now this result is calculated by this value. And when you change this contact angle, it will change the shape and the final state contact with the wall boundary. And now because the simulation time is very short, so I can show it. We changed it to 150 and we run it. Okay, because when it's newly installed, it will cost a long time. We continue to introduce. And the last one is tensile force. Of course, you know the water particles is moving, but it's forced by the tensile force from the air. So the air force is calculated by this coefficient you define. Of course, you can change it. When you change it to a larger one, the force on the water particles will be larger, and the shape will change seriously. And then here are many classes. They are just like the first exercise, the inner code. We define different geometry about the body shape. The first is define the water block shape. Then this two class is about the wall boundary shape. Because we use Boolean algorithm to get the final geometry we want, so we should define the outer wall shape firstly, and define the inner wall shape secondly, and finally we uh, uh, use use plane shape to get the final shape we want. And here we need to define the body type because our water belongs to the fluid body, so we need to define it. Okay. The procedure is running. Okay. Now, this result is calculated by the last value we define, and now we reload it. My software is dead. Okay, we continue to introduce the code because the PowerView software is dead in my computer. I cannot show you the result. Then we should define the material about the water. There are many types about the water material in our source code, but we choose the weakly compressible fluid to generate the water. Here you can see this is the density and this is the viscosity. This is the viscosity and this is the sound speed. They are equal to this value on the right hand. These values are defined by you and here. Same to the definition about the water body, we can define the air body. It also belongs to the fluid body. Here you can see two geometry we defined. One is the water block and one is inner wall shape. And I said we use plane algorithm to generate water geometry. Here you can see this is the algorithm, plane options, and subtract. And then is the material definition about the air. Of course, there are also density, sound of speed, and the viscosity. Finally, it's the all boundary. Here is also the geometry definition. In comparison, because the all boundary is the solid particles, so we don't need to define the material about the all boundaries. It's rigid body. It has no deformation in simulation. Okay. In this file, we define all the parameters we need and define all the body we need about their geometry and the materials. And then this is the CPP file. In this file, we define all the algorithms about the computation we need to use in our simulation. Okay. This is the main procedure. The first line, we should define a computational system domain. In this domain, we simulate all the bodies. Here, this is the system domain bounds you define here. And the second value is the particle spacing. you define here. And because we need to set a runtime about our simulation, so this is a variable physical time. It starts at 0, and now our code interrupt by accident, we can restart our simulation. So we need to use the system restart step, but because this simulation time is very short, it will not suffer the interruption by accident. So you don't need to use this function. Here, because we have defined all the bodies in the .h file and in CPP file, we should to initialize all this class. So this is about the water, and this is about the air. All these classes are defined in .h file by ourselves. This is all boundary. Okay. And you can see the difference from these three. And about all boundary, it doesn't contain the material definition because it's solid particles. And this is a top-level map. You should define the relationship among different bodies. The first one is the water-air complex. The water block is the subject body, and it contacts the air block. And in the second one, the subject body is also water block. It contacts with the wall boundary. But in the last two, the subject body has been changed to the air body. So in the first blank, you should write air block, and it contacts with the water block. Here it's the same. And then is the gravity. Because I have said in this simulation, we ignored the gravity on the fluid body, so the gravity value is set to 0 by ourselves. But if you want to see the result with gravity influence, so you can change the value. Change the value here in H file when you defined, change it to the real gravity 1 or larger one 2. It's okay. It's by yourself. And this gravity because this simulation is a 2D case, so this vector includes two factors. The first factor is 0. It means the gravity force in x direction in the coordinate. And the second one means the force u and in y direction in the of the coordinate. And you should pay attention to this This value, when you write, you should write the elective value because the value is uh, is the value uh, matches the direction of the coordinate. If you write the origin value, this force direction matches the positive direction of the coordinate, and in the same. Okay. And then it's the algorithm about the SPH algorithm. The first one is the initial time or initialize or time step. Uh, because in this simulation case where it's multi-phase uh, air and water body, so almost all this algorithm about the SPH, we need to define uh, two times. One is for the water body, and one is for the air body. Then we need to update the density about the water and the air. They are little different because the the density about the water body and the surface particles about of the water body. When we calculated it in their support domain, there is lack of water particles, so the density we calculated will be less than the initial density value 1. So we need to use density summation free surface complex. This is special to the water body when it contact with air or contact with the vacuum environment. And when I calculate the density of the air body, we don't need to care about this issue. We just need use the density summation complex. It's okay. And this is a transport velocity correction complex. When we calculate the tensile force, because some particles will gather, and because of the due to the tensile force, so in the result you can see some void appear in the screen. Um, this is a kind of physical void due to the unstable tensile force. So, in order to eliminate this result, this issue, we need to add a new force on the fluid particles to eliminate this void. This function transport velocity correction complex is created to eliminate this, and then it's about the time step, because we update all the physical the information of particles by a time step. Here we define the time step size. you can see the first one is the time step of the water block, and the sixth one is the time step of the air block. And here in .h file, you can see two parameters. The first one is characteristic velocity, and the second one is the sound speed. What's the difference? You can see here. In this advection time step size, we use the characteristic velocity to calculate the time step size, and in this acoustic time step size, we use this sound speed to calculate the time step size. And in the final loop, you can see here, this dt is calculated from the advection time step. Where in this time, during this time, we calculated some physical information, and here is also a dt is calculated by the sound speed, and this dt its value is less than this dt, and during this smaller time size, we calculated larger physical properties of fluid particles. Okay, this is the difference about these two algorithms, and the difference difference how to use these two velocity. Okay. And then we need to define the pressure relaxation Riemann with O, and the density relaxation Riemann with O. During the simulation, we should to update the density. We should to update the pressure of fluid particles, and then we can get acceleration of the fluid particles. Then the fluid particles can move due to this acceleration, and then we can calculate the velocity of particles. All these particles will change their positions with their velocity, and because their positions has been changed, and the distribution of the particles will be crowded or not. So this result will influence the density of the particles when we calculate. So the second step will update the density according to the pressure result here. So this is the relationship about these two algorithms. We should I repeat it again. We should firstly calculate the pressure of fluid particles. Then we get the acceleration of fluid particles according to the pressure, because we know the pressure will give particles a force, so the particles will have acceleration, and then according to the acceleration, we can calculate the velocity of particles, and then particles will change their positions with this velocity. Finally, the distribution of particles will become crowded or not due to their difference position changes. And so when because the distribution has been changed, this influence the density of particles. So we need to update the density of all particles. Because here are two phases, air and water, and so we need to use the same algorithm and process to update the pressure and the density about the air body. So you can see there are four functions. The first two is to calculate the water pressure and density, and the last two is to calculate the air pressure and density. Because you know the properties of air and water are different, so we calculated them. We should to define different algorithm. So you can see when we calculated the pressure and the density of air body, this name is different from that of water. This is because the algorithms are different, so we need to create different classes. But the function is same. They are both to update the pressure and the density, and then we need to calculate the viscous acceleration about the air and water. When air body and water body they contact with each other, and even air or water contact with the solid or boundaries, they will suffer viscous force from the labor body. So we need to calculate the viscous acceleration due to the viscous force, and then this viscous acceleration will add to the total acceleration of particles. The total acceleration of all particles contains two parts. One is the pressure acceleration, and one is the viscous acceleration. This is the pressure acceleration we calculated here. Pressure relaxation remain with all. Extend multi-phase pressure relaxation remain with all. But we need to calculate the viscous acceleration here. Finally, you can see here these two function. What's the purpose? If you don't use these two functions, it will not influence the result, and it will not influence the way you run the case, because we need to we wanted to indicate the surface particles at the water and the air interface, just indicate the surface particles. So we need to label these particles. So this is a function of these two class. And this one is the surface tension acceleration inner. In surface tension simulation, particles movement will be influenced by the surface tension force. If we don't consider surface tension force, particles move with the pressure force and the viscous force. But in this simulation case, particle moves moves by three different force: pressure force, viscous force, and surface tension force. And finally is the normal with O. This function is to show the normal direction about the water particles. Just to show the normal direction of the normal case. It's also have no influence on the calculation. Above all this algorithms, we have introduced the calculation functions, and then we will introduce the classes about how to output the data so that we can show the animation in pair view or take plot. Firstly, we should to define the in-output class, and then we should to write two body states to VTU. If you use the pair view to show the result of simulation, we need to define the VTU file. But if you want to use take plot to show the result, you can just change here, change the VTU to PLT. It's also okay. But in general, we prefer to using pair view. So we define the VTU by default. And this two class is about the restart function. As I said, when I run a simulation for a long time, the simulation will be interrupted by accident for many reasons, maybe the power of so on, but you don't want to rerun the simulation at the 0 time step. So this function is useful. You can restart to run the case at the interrupting time point. But this case, the total time to run is very short. It's about 10 seconds, and you can change it to 20 seconds. But I think 5 seconds is enough. You don't need to change it to a long time. And this is also for the restart. You don't need to change it because we don't use it. And here we write body states to file. Here we define the function to output the information to VTU, and now we need to write this data in the file. So the peer review and any other software can read the data. And here you can see we define many parameters about the for loop to run this case. But there are only two parameters you should focus on. The first one is the end time. This is the total time you run the case. Here we define it's 10. You can change it to other times. And this D time. D time is the time step you output the data. For example, the end time is 10 and it divides 100. This means one time step is 0.1 second. And during this total time, we output all the data for 100 times. So when you upload the data in peer review, you can see there are 100 files there. And if you want to see the simulation in details, you can change it to 1000. It's also okay. But I think this will cost a longer time to run the case, but it's up to you. If you want to see the result carefully and okay, you can change it to a larger value. Here is the for loop to run the case, and the first is the while. You can see the fifth time. The fifth time, this value we defined here. Here you can see it. It starts at 0 seconds. So the total runtime is judged by this one. The fifth time should be less than the end time. If it exceeds the end time, the simulation will stop. And as I said, in this case, we define two time step size. One is the advenction time step here, and another one is the acoustic time step size is calculated by the sound speed, and the advenction time step size is larger than the acoustic time step size. So you can see this for loop judged by advenction time step contains this for loop judged by the sound speed time step. In this two loop, we calculated different physical information about the water body and air body. Firstly, we can see we calculated we initialized our time step, and then we calculated the advenction time step, and here we choose the minimized one value to calculate the other physical information later. Here we update the density, and then we calculated the transport correction to eliminate the physical voids caused by the unstable tension force on particles. And then we calculated the viscous force of the air body and the water body. You can see in total there are 4 physical properties should be calculated in this for loop during the advection time step. And in the smaller acoustic sound speed time step, we calculated other properties about the fluid. Here we get the sound speed time step size. Because the sound speed of air and water are different, so we need to calculate these 2 sound speed time step separately. This is also the function to choose the minimized one. Here we can see the surface detection and the corner gradient. These 2 functions is just to indicate the surface particles. It will not influence the calculation in simulation. So we can, because of these 2 functions, we can identify the surface particles from the internal fluid particles. And this weighting norm is to show the normal direction of water particles. And here we calculate the surface tension acceleration and water pressure and air pressure, and we update the density and the air density. As you can see in this smaller time step, we mainly calculated the force, the tension force, pressure force, density change, and when we calculate the pressure and the density, we all of them use the dt to calculate. And finally, here is the time step data to show on the screen. N is the number of iterations, and time is the physical time it cost, and dt is the advection time step, and this dt is the acoustic time step. And finally, because after one time step, all the distribution of particles and all the physical information of particles has been changed, and so we need to update the cell link list. The function of the cell link list is to store all these new standards of all particles, and for the next update in next time step. Here is to update the water body, and here is the update the contact relationship between water and air, and this is the update the relationship between water and wall boundaries, because you know as the time goes on, one fluid particle in different time step, it will contact with different air particles and different solid or particles. So we should so besides we update the water particle itself, we should also update its labor particles of the and this is same to the air body. This is to update the air particle itself, and then we need to update the labor particles of air particles. And finally, okay, I think this is all. Do you have any questions?
I think you can show your simulation results to our from your preview if you have that.
Yeah, I think I should show the result in preview, but my preview is dead in my computer. I cannot start it. But I think firstly, I have shown the result about the surface tension. Everybody, I think they have watched it. Yeah.
I think I can try it.
Everybody, do you have any question? If you don't have any question, I will show you another case. Another case.
对，我现在在搞。
Anyone, do you have any question? If you don't have any question, I will tell you what you can change in this case file. In this .cpp file, you don't need to change anything because it involves all the algorithms when we calculate. If you change some of them, maybe the case cannot be wrong. But of course, if you are interested in these algorithms, you can change it, and then you recover to the default version. It's okay. And in our suggestion, you can change all this parameter definition about the geometry of the body and the physical properties of the fluid body and the solid wall boundaries. And you can also change the geometry shape of all bodies. So in total, all the things you can change is contained in the .h file. Okay. If you don't have any question, I think this exercise is over. Everyone can leave this room.
Thank you.
Okay, thank you. Do you have any question, Benjamin?